Hi, and welcome to my ENGG104 presentation on reactance in capacitors and inductors. First up, I'll just quickly go over what capacitors and inductors are. So a capacitor essentially consists of two parallel conductive plates with a dielectric material between them. This causes charge to build up so that each plate has either a positive or negative overall charge. This causes energy to be stored in the electric field between the plates. An inductor also stores energy, but as a magnetic field. When there is current, a magnetic field forms around the wire. An inductor is just a coil of wire that stores much more energy than a single wire would. This common characteristic of storing charge is what leads to reactance. To make things less confusing, here's a little comparison table. Resistance, reactance, and impedance are all related by the opposition of current flow, which is why they all share a common unit of ohms. Resistance exists in circuits with only resistors. Reactance exists in circuits with either a capacitor or an inductor, and the impedance occurs when we have a combination, i.e. in RC, RL, or RLC circuits. Reactance is more specifically when charge is stored and released in the direction opposite to current. Impedance is a combination of capacitive and inductive reactance with DC resistance. Here's the formulas for each, where F is frequency and L and C are the inductance or capacitance respectively. We can substitute this 2πf for omega, or the angular frequency. Taking a quick look at the effective frequency, which comes from AC circuits, we can see that increasing frequency increases inductive reactance and decreasing frequency reduces inductive reactance, and the opposite of this is true for capacitors. Since AC current involves complex numbers, we can represent these reactance equations slightly differently. Introducing J allows us to represent the reactance and impedance in polar form. Looking at this graph makes it easier to understand, and most calculators also have an automatic conversion to polar form, where you just have to input the real and then imaginary part of the expression. Here's a really quick example that you can test on your own calculator. Finally, I have some really quick examples for calculating reactances. For the first one, we're given all the information that we need, so all we have to do is plug it into this 2πfl equation. Converting to SI units will give your answer in ohms. Secondly, we have a capacitor and inductor in series. Using our formulas, we know that total reactance is just the difference of the inductive and capacitive reactance. Once again, we're given all the information to plug in, and this is our final answer, 122.9 ohms. That's just a really brief overview of the topic, but thank you.